Yeah, the first thing is to thank the organizers for inviting me to give this iTrain. I think we'll have fun with this simulation exercises. And let's start. So I will share the screen. I hope it still works. Do you see the screen?
Yes.
Okay, fantastic. So for those of you who want to use the code, we have prepared two different ways of getting it for this iTrain. One of them would be to load a virtual machine that we have shared with you. You have the link to the virtual machine. And another one is to download the code directly from the internet and run it natively on your computer. Okay, if you just Google for APSYNSIM, then I think the first link that you will find is this one, which is the project files for download. Okay, so there are different releases. In the last few months, there have been a bit of movement because Matplotlib was changing a lot of things, and the code stopped working. Then I had to move to Python 3, which was painful. I'm very sure that bugs have appeared because of this translation and so on. But I think that we have a running code now that works on Python 3 and also on Macintosh. Okay, there are some updated instructions to make the code work natively on Macintosh. I've been trying to upload a new revision of the release just this morning with these updated instructions, but Launchpad is not working now. But I will upload it as soon as I can. Okay, so you should see soon, you should see a new download file here, which is a revision of this release with updated instructions on how to install and run it on Macintosh. Okay, so whatever the way you want to try, the code should in principle work in Linux, in Mac, and eventually, if you are able to install Python in Windows, also in Windows. And if you have any problem, please tell me. I will try to update the code and help you to fix things as much as I can, because I don't have Windows. Okay, so let's start now the virtual machine. I will run the virtual machine. Okay, so those of you who have downloaded it, you just run VirtualBox or VMware or whatever virtual machine reader that you have installed. Then the machine will start. It takes a little bit of time. It's a lightweight Linux distribution, but it takes a bit of time to load. You see, now you hear the beautiful music. And there is this button here that I have added to the desktop that allows you to get a little bit more resolution. Yeah, because the screen that comes with a virtual machine for some reason is not able to make it big. But if you press that button, you will see that the screen will become much bigger. And now if you want to run APSYNSIM, just press this button. Okay, this green button here at the bottom left corner. And from all these options, you see here APSYNSIM. Actually, it's not well written. This should be an M, APSYNSIM. And there is another software called APSYNTRUE, which we may not have time to run in this session, but I assure you it's very fun. It's similar to APSYNSIM, but it works with real data. And there are some examples of real data, like the EHT images of M87, some VLBI data, some ALMA data as well. And you can use this very nice graphical interface with lots of interactivity to play with the real data. But now what we are going to do is to deal with APSYNSIM, okay, the simulator. So if you just click on it, you will see the simulator appearing on your screen. If you are bothered of these spaces that are left here, just double click a couple of times here at the top, and then the full screen will be filled. Just tiny things, okay? And this is the main screen of the simulator. Yeah, so we have different, well, the screen is quite busy, but let's explain a little bit what is each thing here. So on the one hand, here at the top left, you have the array configuration, which is the spatial distribution of the antennas. Okay, this is your interferometer as it is seen from the zenith, okay? So from top of the observatory, okay? You can add antennas, subtract antennas, you can move antennas. If you just click on the mouse and drag the antenna, you can move the antenna, and you can see in real time what happens to everything else, to the UV coverage, to the dirty image, to the PSF, okay? So it's very fun actually to play with this with this antenna distribution and drag antennas and play with it. Okay, array distribution. This plot here is the UV plane. Is basically the Fourier transform of the source structure. So this is Fourier space. Okay, this is not ordinary space. This is Fourier space. And in grayscale, you have the amplitude of the Fourier transform of the source. And in green, you have the locations where your interferometer has taken measurements. Okay, these are the what we call the UV points. Okay, these are the baselines projected into the plane perpendicular to the source direction, basically. Okay, the points of the Fourier space where the interferometer is taking measurements from. Actually, you can zoom in and zoom out from all plots by just pressing capital Z and small z. Z, the first letter of zoom, okay, the Z letter. If you press capital Z, which means Shift plus Z, you will zoom in. And actually, you can zoom into any position where the cursor is pointing. Okay, so if the cursor is hovering over the UV plane figure, then you will zoom in the UV plane figure. If your cursor is zooming on the array configuration and you press capital Z, you will zoom in the array configuration, and so on. You can zoom in the PSF, you can zoom in the images, the model image and the dirty image that I will describe in the following minutes. Small z, so I mean z with no capitals, will zoom out. Okay, so in the end, just zooming out a little bit to come back to the original. Yeah, okay. So this is the UV plane. Then the dirty beam, this is the Fourier transform, is roughly the Fourier transform of the UV coverage. I say roughly because it depends on the weighting of the visibility zone, how you weight the visibilities when you grid the Fourier space in order to come back to the image plane. Okay, doing this fast Fourier transform. Depending on how you grid your visibilities, how you weight them, you may get a slightly different results. We will play with this. Okay, we'll have time to play with this and discuss the different weightings. Here you have the model image. This is the true image with infinite resolution. Okay, you will have, actually you have different models that you can load, and you can also define your own models. You can take an image and convert it into a model for APSYNSIM. It's very easy to do. And you can add geometrical structures to images. I could add a disk here or a point source here. You can combine sources in very different ways. It's very fun to do. And here you have the dirty image, which, as you know, is the convolution of the model image with the PSF. So if you take this model image and substitute each one of the pixels of this image by a scaled version of the dirty beam, what you have is this, okay, the dirty image. Here you have some controls which allow us to play with the geometry of the interferometer. Here we can change the latitude of the array, take into account that these arrays that APSYNSIM is simulating are small arrays. The baselines are not long, so that means that these antennas are assumed to be coplanar. Okay, so that means that we're assuming that the Earth is flat within this region. Okay, we know that the Earth is not flat, but we are assuming coplanarity of the antennas in the array. So that means that we are forced to have small interferometers in APSYNSIM. We cannot simulate VLBI in APSYNSIM, not yet. I have a plan to do it, but I didn't have time to implement it. So all the arrays are small. That means that they can be defined by a single value of latitude, because all antennas are so close together that they share the same latitude and longitude, roughly. Okay, here you can set the latitude of the center of the array, which is, as I told you, is very similar to the latitude of the rest of the antennas. Here you can change the declination of the source. Here you can change the hour angles, the starting hour angle and end hour angle of observation. Hour angle, as you know, is the time spent for the source to cross the meridian of the observatory, or the meridian, the place of the observatory. So that means that hour angle 0 is when the source is at maximum elevation. Okay, it's just transiting. That means that in the case of this simulation, the initial hour angle is minus 2.15. The final hour angle is 1.5. That means that the observations took 3 hours. 3 hours from minus 1.5 to 1.5. 3 hours centered at the transit of the source. Okay, this is what we are saying APSYNSIM to simulate. Okay, when we set these numbers like this, it's 3 hours centered on the source transit. Here we can change the wavelength, the observing wavelength. We can go to 3 millimeters, to 1 millimeter, or to centimeter wavelengths just by playing with this slide ruler. And the robust parameter, which is related to weighting, how you weight the visibilities when you grid them in order to make the image. We will play a little bit with the robust parameter when if we have time. I hope we will have time for that. Okay, so this is how APSYNSIM, that's the meaning of the main window of APSYNSIM. There are more windows that well, maybe we'll have time to show. But first things first, let's first play a little bit with this simulator using ALMA observations, simulated ALMA observations. So the first thing I would suggest is to load a suitable model for ALMA observations, which is like this nebula. This is called nebula. Okay, is this image here, nebula.model. Just press load model. This allows you to load any model. Okay, you see that the catalog, there is a nice catalog of models in APSYNSIM. You can add your own models. It's very easy to add. Okay, just read the instructions and you will see it's very easy. You have radio galaxies, point sources, disks, Gaussians, you have everything. Okay, and there is a version of this nebula that is much smaller, which is suitable for ALMA, because look, this nebula is huge. It has 400 arc seconds of diameter. Okay, there is another scaled version of this nebula that is more suitable for ALMA, which has 60 arc seconds, okay, diameter. And now we load the ALMA array, okay, but since I would like to focus this first exercise to explain about what the details, the gory details, and some things to take into account when you combine data of ALMA main array with ACA. First, I would like to load the main array only. So I will load a version of the ALMA main array, which is configuration 5 used in cycle 1. It's very old, okay, but that's the array that we have here. You can add your revised versions of the ALMA array here. So we will observe with configuration 5 ALMA cycle 1. Okay, just select this and click open, and then the main ALMA array will be loaded. So this is how ALMA looked like in cycle 1 configuration 5. And this is the observation of this nebula at 1.65 millimeters. Okay, this is the latitude of ALMA. This is the declination that we have set for the source, minus 45 degrees. We are observing 2 hours focused on transit or centered on transit. Okay, and robustness parameter, which is set to 0. We will see what it is. Okay, we'll have time to explain. Okay, notice what happens here. So this nebula has some compact structures here, which are very bright, very clear, and they are actually seen by ALMA. But there is also extended structure. This is a bowl of very extended diffuse emission surrounding these compact structures that, as you can see, are not seen by ALMA. They are seen as a kind of negative bowl. We are not sensitive to this extended emission. This negative bowl here is what we usually call the missing flux effect. And the way to understand it, or in order to understand it, one thing we can do is to go to Fourier space. Okay, so let's zoom in to the center of Fourier space. And as you can see, this grayscale, which I remind you is the Fourier transform of the nebula, this grayscale is dominated by a very compact lobe in Fourier space. Okay, this compact lobe in Fourier space, as you may remember, something which is compact in Fourier space is extended in the image plane and the other way around. Okay, so this compact lobe here is related to the extended structure of the nebula, and it is actually dominating the amplitude of the Fourier transform. That means that the extended contribution of this nebula dominates over the compact emission. And as you can see, the shortest baselines of the ALMA main array are unable to sample this lobe. This is what is producing this negative bowl here. Actually, if you click on any of these short baselines, you click on these green lines here, the code tells you what is the value of the amplitude, the phase of the visibility, and the baseline, 10 to 13, okay, and even the hour angle of observation. So 10 to 13. Actually, it's here. Let's zoom in the array. And you see here, so when you click a baseline, actually APSYNSIM highlights the baseline. So yeah, you can identify points here with array here. Okay, let's click on another baseline. This is a little bit longer, and this baseline is 4 to 3, observed at -1 hour angle as well. Okay, so this tells us that, of course, we have short baselines in ALMA, like 10 to 13, 4 to 3, but these baselines are not short enough to sample well the main lobe of the Fourier transform, which is related to the extended structure of the nebula. Okay, what happens if we observe with the ACA? So let's load the ACA. Press load array, select ACA.array, and open it. So this is the ACA. And now the situation is completely different. If you zoom in, you see that the ACA antennas are sampling a good part of the main lobe of the Fourier transform of the source. Of course, not the whole of it, because we would need total power to actually sample the central pixel, which has the peak of the Fourier transform. But unfortunately, APSYNSIM doesn't have the simulation of total power implemented. Okay, the idea would be if you want to retrieve information about the center here, you will need total power image. Yeah. But anyway, you see that even though we don't have total power, we are able to scan, to sample the Fourier transform of a good portion of this main lobe here. Yeah. And as you can see, the baselines are much shorter. The baselines of the ACA are much shorter than the baselines of the main array. Now, what can we do to have the best of both worlds? To have the angular resolution of the main array and then the sensitivity to extended emission of the ACA. One thing we can do is actually what we usually do is to combine the ACA with the main array. Okay, so here you have an example of ACA plus main array, where there are two combined. So APSYNSIM is able to combine two different arrays, two different disconnected arrays. That means that you have baselines among the antennas of the first array, baselines among the antennas of the second array, but you do not have any common baselines sharing antennas of the different arrays. They are disjoint arrays, okay, but they are observing the same source. So we can combine the data of the different arrays. Okay, this is what we do when we combined ACA, which now appears in red, and the main array, which now appears in green. You see that? Well, there's still this ball here. we will come back to it. It depends on the weights that you assign to each one of the arrays. But let's first take a look at the center of the Fourier plane. Now zoom in, pressing capital Z. And as you can see, it's beautiful, isn't it? So we now have a good sampling of long baselines, which give you information about the small structures of the nebula. And at the same time, you have the ACA sampling a good portion of the lobe. And what is very important here, you have points in your space where you have close observations with the main array and with the ACA. So in this point here, for instance, if I click here, this is baselines 37 to 38. 37, 38, if we zoom in, this will be an ACA baseline. You see? Is this one? This baseline here is one of the longest baselines of the ACA. You see? It's one of the longest baselines of the ACA. And if you click here, this will be one of the shortest baselines of the main array. So the shortest baselines of the main array, let's say, overlap with the longest baselines of the ACA in such a way that you can use these overlapping portions of Fourier space to scale the amplitudes of the two arrays. This is very important. You need some overlap of the two arrays in order to be sure that you are scaling the visibility amplitudes properly. Because you know that the amplitude, the accuracy of the amplitude calibration of ALMA is relatively good, but is not perfect. And especially if you observe with the ACA and main array in different days, under different atmospheric conditions, even using different calibrators, the final amplitude calibration may not be well aligned between the two arrays. And one thing you have to do in order to avoid possible artifacts in your image reconstruction is to be sure that you share some points in UV space of the two arrays, and you use these common regions in Fourier space to scale the two arrays together so that they match. Also, there are other problems which have nothing to do with the amplitude calibration, but with the phase calibration. You can have astrometry offsets between the ACA image or the ACA data and the main array data. And you can also use these common points here to actually solve for these plane wave additions that you have between the ACA and main array. But of course, I think that to do such a thing, I think that would go beyond QA2. I'm not sure because I stopped working for ALMA quite a while ago, but I think that to do this fine, gory detailed calibration of array combination, you would require a bit more than QA2. Please correct me if I'm wrong. Yeah. So now, why do we still see this negative ball here, even when we are combining ACA and main array? Well, that has to do with the relative weights that we assign to the visibilities of the different arrays. Pay attention because this is subtle. One thing is the visibility amplitudes. You have to tune them to match. These are the numerical values of the visibilities, the amplitudes. You have to scale them so that they match in the overlapping regions of Fourier space. This is one thing. They are values of the visibilities. A completely different thing are the weights of the visibilities. That means their contribution to the final image. Okay, this is what you said here in APSYNSIM. And this has to be done in real cases. It has to be done before you combine the data for the imaging. You have to decide, you have to select what way or which weight to assign to each of the arrays. If you overweight the ACA, your image will become more sensitive to extended emission to the expense of a loss of resolution, and the other way around. Yeah. So statistically speaking, the optimal value of this ratio between weights should scale with the different sensitivity of the antennas, right? So if I remember well, this should go something as logarithm of 12 over 7 squared, which is 2 times the logarithm of 12 over 7. But I think there was another factor there that I don't remember now. Maybe Sebastian or Carmen or yeah, we'll remember. So you play with these values. If you now set these to small values, that means you are overweighting the omega 2, the weight 2, which is the weight of the ACA. Remember, the main array is array number 1. The ACA is array number 2. Okay, so if you decrease this number, you are overweighting the ACA. Looks what happened to the image. So the image lost information about the higher spatial resolution. Yeah, basically ALMA has very little to say here because it weighs more than 1,000 times less than the ACA when we set the weights like this. Look what happens to the point spread fraction. Something very, very odd happens here. You have kind of a superposition of 2 beams. One which is narrow, is like a pencil, is the main array beam, but you have a plateau. You see the plateau? You have a plateau surrounding it that is basically the beam of the ACA. And deconvolving an image with a beam as ugly as this is very, very troublesome because the units of Janskis per beam are not well defined anymore. You have a plateau that is biasing the Janskis per beam. When you reconvolve the image with a clean beam, all the effect of the plateau is gone and your image is strongly biased. There was a project, actually, a project with real ALMA data. I don't remember the PI, but I was the contact scientist of that project. And we had such a problem. The beam was very ugly. It had this narrow beam and then you have a huge plateau. And the deconvolution was horrible. Clean wasn't working because the beam was not fitable to a Gaussian anymore. You had these 2 Gaussians, a narrow one and then a very wide one, which was introducing that plateau. Okay, so if you now go to large numbers, then the main array weights more than the ACA, and well, you have resolution, but you don't have the sensitivity to extended emission. And if you go somewhere in between, let's put it this way, that's minus 2.5 or so, then you have the best of both worlds, right? You start to become sensitive to the extended emission, and at the same time, you haven't sacrificed much resolution. Yeah, so is there any question or comment until now? But I wouldn't like to accelerate and go further if there are some doubts. Maybe we can solve them interactively. Is there any doubt or thing that you would like to comment?
No one has posted in the Q&A, but if people want to, definitely feel free to post in the Q&A throughout the talk, but there's nothing there now.
Okay. So, okay, now let's play a little bit with the robustness parameter, because when you use robustness parameter, when you change the weighting scheme of the visibilities with a combined data set, there are the interesting things that can happen. Yeah, okay, so if you select, for instance, a uniform weighting, which means robust close to -2 or robust -2, this means uniform weighting. What happens is that all the pixels in the visibility space, all the pixels of the gridded visibilities, you take your Fourier space and you grid it, all the pixels weight exactly the same. So it doesn't matter how many visibilities you have in each pixel. It doesn't matter how sensitive these visibilities are. We don't care at all. We assign the same weight to all pixels, which sounds a bit odd, right? But has many advantages, because if you weight all pixels equally, you are like optimizing the effective UV coverage. You are using all data the same way, and your UV coverage is effectively maximal. Okay, you are taking the most of your UV coverage. That means that the PSF is usually more beautiful. The side lobes are usually smaller because you have more effective UV coverage, and you have more resolution because the long baselines weight quite a bit. It doesn't matter how many short baselines you have, how packed are them, because they will weight the same as the long baselines. That means that you have a narrow middle. But you sacrifice things as well. We will discuss about this later if we have time. But now focus on this. Let's focus on this. Let's make the ACA weight a little bit more. Yeah. And now robust parameter is set to -2. Now let's do one thing. If you press now the key U, okay, the U, the first letter of the word unicorn, U, this window will appear. Okay, so this window are the Fourier transforms of all the images that we see here. Okay, so this is the Fourier transform of the PSF, which should in principle be the UV coverage, but is the UV coverage with the proper weight. Okay, this is a gridded UV coverage where each pixel has a weight assigned to it. This is the Fourier transform of the observations. That means that this is the visibilities, the gridded visibilities, and this is the Fourier transform of the source. So this corresponds to the grayscale here. Yeah, we can zoom in. Let's zoom in. Okay, so one thing we see is that when we apply uniform weighting, you see all visibilities basically weight the same. Well, there is a little bit of offset here at the very center. That's because robustness parameter is an approximation to uniform weighting. Okay, robust -2, we used to say that it's uniform, but it's not exactly uniform. It's an approximation to uniform. The exact uniform is when robustness tends to -infinity. Okay, but in usual cases, -2 is good enough to assume that it's uniform. But in this case, the weights are so different. The difference between the weight of the ACA and the main array are so huge that -2 is not a good approximation anymore to uniform. So it's almost uniform, but not uniform exactly. But anyway, the difference is not that big. Okay, you see that all baselines are weighting more or less the same. And then you have these UV, the observed visibilities and the source. Well, they look similar, with the difference that you don't have a point here at the very center, and we don't have the total power observation. Now, let's change robustness parameter to the other side. Let's make it natural. So natural weighting is a completely different philosophy of weighting. In natural weighting, what we do is to assign to each pixel a weight which is let's call it the rigorous statistical weight that we have to assign. Okay, so it's the weight determined by statistics, by mathematics. What do I mean by that? So the value that you will have for that pixel and the weight that you will have for that pixel will be such that the average that you will have there will have an expected value that will be the mean value of the population of all visibilities that would be on that pixel. So that's the mathematical definition, right? that you would have to use when you do averaging, and the weighted averaging actually. So if you do that, if you do things in the rigorous way from the point of view of statistics, the price that you get is that your sensitivity is optimum. So you are extracting all the signal you can extract because you are minimizing the effect of noise by doing this. If you do the things statistically correct, then the effect of the noise will affect in a minimum way, or will bias in a minimum way, the actual measurement. So your data become more sensitive. We will see an example of this. Be patient. We will see a very beautiful example, actually, where we will see the huge difference between uniform and natural when you are limited by sensitivity. But see what happens. See what happens. When you assign robust natural, look at this. So the effect of this plateau becomes even more clear. Yeah, it becomes even more clear. What happens in Fourier space? If you go to Fourier space, you reload, you see now the contribution of the long baselines. Yeah, let's zoom out. Now I'm zooming again. You see the effect of the long baselines on the PSF is minimum. You see, they are almost gone. Yeah, because all the weight is spot to the ACA. Yeah, because the ACA is weighting more. We have forced that their statistical weight is more, and that automatically adds much weight there, and basically we are starting to be dominated by the ACA beam. That's what is introducing this plateau here. So the takeaway message from all these experiments is, when you deal with data that has been combined between main array and ACA, beware of the weighting scheme that you apply to your visibilities. Usually, as far as I know, maybe things have changed, but ALMA Observatory uses for the QA2 0.5. Is it still the same? Is it still 0.5? So 0.5 is a kind of good compromise between uniform and natural. It kind of gets the best of both worlds. Yeah, it has a little bit more sensitivity and doesn't sacrifice much resolution. So you have a good trade-off. But in special cases, you may be interested in using different values than the standard. For instance, in experiments where you are aiming to detect something, when you are limited by sensitivity, you may be interested in moving to natural instead of the standard QA2 value, which is 0.5. Okay, so what can we do now? One thing we could do is, let's go to the clean window and let's play a little bit with cleaning, if you don't mind. So I will just by eye, okay? I will just assign a weight here that I see it's okay. We are sensitive enough to attend the emission, and we don't lose much resolution. Maybe this one is a good one. This relative weight between the main array and ACA. And let's go cleaning. So we can do cleaning. If you press the button reduce data, so a window will appear where you can clean. So this is not a super nice cleaning. This is not a cotton swab clean where you do major cycles, minors. No. This is very simple vanilla clean where only minor cycles are done. But it's just for fun, okay? This is just for having fun, yeah? So here you can define the clean gain, the number of iterations, the threshold for cleaning. And I will explain you a little bit these buttons. We will play a little bit with it. So first things is to make a clean mask. Okay, so if you just click and drag with your mouse with the left mouse button, you will create masks. Okay, you will create masks. If you want to remove a mask, the way to do it is to click and drag with the right mouse button. You see, I'm removing masks. Yeah. I know that in Macintosh you don't have right mouse button, and I actually have no idea how you can emulate a right mouse button. So it may depend on how Macintosh interprets the event of right mouse click. I'm very sorry I don't have that information for you. But yeah, this is the way you can create masks. And then if I press clean, you will see how clean happens in real time. This is very pedagogical. You will see how the PSFs disappear from the dirty image and clean beams, I mean Gaussians, appear in the clean model image. So if you press clean, you see how clean is removing all the flux from the dirty image. So PSFs are being removed from here, and clean beams, that means Gaussians, are appearing here. It's very nice. Actually, while we are cleaning, you see that the peak brightness of the dirty image disappears. So if you want to see the whole color scale again, you can press rescale. So this hasn't changed the dirty image. It has changed the representation. Okay, the color palette. The color palette has been rescaled so that you can see better the peaks. Yeah. Let's clean a little bit more. And now you will see something that usually happens to clean if you want to clean extended emission. Clean uses to produce clumpy image reconstruction. When you are cleaning extended diffuse emission, clean usually makes things clumpy. Yeah, it's cleaning. It goes slow because it's pedagogical, right? The idea is for you to see in real time how this happens. That's why it's slow. It's drawing every time all images. That's why it's slow. Okay, this is 100 iterations. There's quite a bit to be cleaned, yeah, but still there's some structure here that we can already compare to the true image. You see that the structure is kind of being recovered. We start to see this void here, which is this void here, this void here, which is this void here. Yeah, but this is the model free of residuals. Yeah, if you want to add the residuals of the dirty image to your clean model, you just press this button, which adds the residuals or subtracts the residuals. Okay, so I will clean a little bit more. See, the ALMA beam is so beautiful that even the clean model resembles the dirty image, yeah? Because it's so beautiful. We have so many antennas. Okay, it's cleaning. We'll finish soon. There's a lot of extended emission. I will not go further. So one interesting button here in this interface that you have is this button called Show FFT, which shows you, it's similar to the U button when you press the U button in the main window. Here it shows you the Fourier transforms of all quantities involved in this process. Okay, you have again the Fourier transform of the PSF, which is the gridded version of the visibilities with the proper weights. You have the Fourier transform of the clean model. So this is how clean is interpolating in Fourier space. This is the Fourier transform of the source. This is the Fourier transform of the source convolved with the clean beam. And this is the Fourier transform of the clean model convolved with the clean beam. And these are the residuals. So as you can see, this extended emission that is remaining here that has not been cleaned is here. These are the residuals in UV space. Okay, so it's the ACA what remains to be cleaned. All the short baselines of the ACA, which are still to be cleaned. We should clean deeper and deeper and deeper in order to start getting rid of all this extended emission that is dominating the residuals in the short Fourier spacings. But as you can see, wow, it's doing something. So clean is kind of interpolating the visibilities even in the zero spacing. So you see that clean is interpolating a net flux density here at the very center of Fourier space. Yeah? Clean usually does a nice interpolating job in Fourier space. but in cases of very complex sources like this one, where you have extended emission, where it may have some problems. So another interesting button is the restore. So this is the clean model with no convolution. So this is the clean deltas. These are the clean deltas with no beam, with no clean beam restored. And if you press again, you will convolve them with the clean beam. So this is the clean image. So beware of how we call things, okay? The nomenclature that we use. Beware because sometimes I've been discussing with people and we were talking about different things because we were not using the same nomenclature. This is the clean model. This is made of deltas, of Dirac deltas. Janskis per pixel are the units of the clean model. And this is the clean image. This is the clean image. Actually, in order to have the clean image, you usually add the residuals. Okay, so you add the residuals to this, which is not mathematically rigorous because you are adding apples to oranges. You are adding something that is convolved with a PSF. You are adding it pixel to pixel to something that has been convolved with a clean beam, and these are not the same. Yeah, but we usually do that. We usually do that. Basically to give an idea of the noise, the contribution of the noise. So it's not mathematically rigorous, but it's done. So, okay, this addition of the residuals. Okay, so again, this is the clean model, and this is the clean image with the residuals added, if you prefer. So pressing all these buttons allow you to plot different things. If you press this button, true source convolved, it will open this window, which is what clean should recover in an ideal world. This is the true source, I mean the true image with infinite resolution convolved with the clean beam. Okay, so this is what clean should recover if it would work perfectly. The true source convolved with the clean beam. And as you can see, well, it's not the case. Yeah, because clean tends to recover some, to introduce some clumpiness, yeah, in the image reconstruction. But if we would clean deeper and deeper, maybe we would start recovering a little bit of this here. Yeah. Okay, so what else? Any questions, any comments to this point? No?
Ivan, I have just a quick question.
Yes.
You have a number written. Was it the total flux in your map or what?
What is that? Is this one?
No, in the source convolved with the clean beam.
Source convolved with the clean beam.
So there you have this number. Yes.
Yeah.
Yes.
Yeah, I forgot to explain. So if you click on any point of this image, it will tell you the right ascension, declination offset, and it will tell you the value of the flux in Janskis per beam, because this is convolved, it's Janskis per beam. Yeah. As you can see, the units are huge because the nebula model is very bright. It has many Janskis. Okay, that's why you have so large numbers here. So this is Janskis per beam, yeah, because it's convolved. You just click on any point. Actually, this is very handy when doing exercises with APerture SYNthesis, and you estimate the size of the beam. And I ask the students to just click on different pixels of the PSF and check where the PSF decreases to 0.5, which is half the intensity. So yeah, these numbers here, yeah, are basically telling you locally what happens in the image. So what's the delta alpha, delta delta, okay, and so on. And here it also gives you the fit of the PSF to the clean beam, which is very round, as you can see. Yeah.
Would you have a way to measure the total flux that you recovered during your?
Yeah, the total flux is here.
Okay, perfect. And
So
that we can compare to
1,000
the
Janskis, 1,600 Janskis, and even more because there's a lot of extended emission to be cleaned. So yeah, the nebula model is very bright. Yeah, it's not very realistic. Yeah, but well, that's the way I made it. But you can change it. You go to the model file and you can add a common factor to all pixels and decrease it and make it much weaker. Yeah, but this is the total flux. Yeah. And actually, if you go, let's quit the clean window. If you go here and you click, you see, it's the same thing. So it tells you where you are and what's the intensity in Janskis per beam. So in the case of the PSF, let's zoom in. If you click at the very center, it's 1. So the PSF is normalized to 1. This is why when you clean and reconvolve, the units are Janskis per beam. Because if you observe a source that has 1 Jansky, you will see a PSF, an actual PSF, because the peak will be 1 Janskis per beam, which is the peak of the PSF. Okay, this is the trick that allows us, when we are weighting and reweighting and normalizing the weights of the images, when we clean or when we deconvolve. It's not just clean, it's any other deconvolution algorithm. When we normalize the weights, we are doing this. We are converting pixel units into Janskis per beam. And that's the reason why, because the PSF is scaled to 1. And if you go to the dirty image, you have the same thing here. Okay, so you have the value of the dirty image and the delta alpha and delta beta. Yeah. Okay, so I think one thing we could do now, which I promised you that we would do, is to play a little bit with the sensitivity. So let's observe something that is very weak and see what happens. So I would suggest you to load a new model called point source. If you load the point source, there is a point source here. There's a pixel. It's just 1 pixel. Why? You don't see it because it's very small. But if we zoom in, remember Shift Z, capital Z. If we zoom in, do you see the pixel? It's a point source. Okay, let's zoom out. So what you see basically is a scaled version of the PSF, which is shifted to the location of the point source. Let's increase the observing frequency. So we have more spatial resolution. Band 9, yeah, 0.3. Let's go to 0.3. Now we have band 9, yeah? Is it band 9, by the way? Is it band 9, right? I should know, but I've been working with ALMA so many years, but come on, sometimes my memory starts to fail. Okay, so this is one source which is very bright. It's 1 Jansky. And ALMA, in the first approximation, has infinite sensitivity, right? So we have no problems in detecting this source. But let's add some noise. Now, if you press the button Reduce Data, one of the other interesting things that you can do here in this window is to add noise, because all the simulations we have seen so far are noise-free. So all the noise that you see in the images is not thermal noise, it's noise related to the effect of PSF, it's convolution noise or dynamic range limitation noise. Okay, this is has nothing to do with thermal noise. If you want to add thermal noise, you have to add a number here, write a number here in Janskis per beam. So this is the expected sensitivity in the image plane. And then just press the button Redo Noise. So since the source has 1 Jansky, first things first, let's change robustness parameter to -2. So I will use uniform weighting. Yeah. So I will reload. Now this is the image with uniform weighting. We are using uniform weighting. Remember, all pixels are weighted with exactly the same in exactly the same way. Now the source has 1 Jansky. Okay, let's add a huge noise. Let's add, for instance, if we want to have a 5 sigma detection, we should add like something like 0.2 Janskis per beam, right? 1/5 of the peak. If we add 0.2, we should in principle expect to see here a 5 sigma detection, isn't it? That's what we expect to see. But if you press the button, wow, well, kind of, yeah, but wow, I wouldn't believe this detection. Yeah? It's definitely not a 5 sigma detection. What happened here? What's the problem? Is it a bug in the code? Did I make a bug in the code? No, there's no bug. There's no bug. This is because the way you are weighting your visibilities. So I told you that now if you go back to the main window, you will see the image has been updated with the noise. I told you that if you use uniform weighting, you have optimal resolution. You have a very nice PSF with low side lobes, which allow you to recover high fidelity clean models because the PSF behaves better. The side lobes are lower, but the price to pay to the expense of sensitivity. You lose sensitivity because the way you weight the visibilities is not the rigorous statistical way. So if now you go from robust -2 uniform, you go to, let's say, robust 0.5, which is the one used in the standard QA2. Yeah.
May I comment it now, because you mentioned this, you asked this before, and
yes,
it's relevant for this. So nowadays, when we reduce ALMA data, a telescope reduces ALMA data, it tries to follow both things. The PI has a requirement on the beam size, but also on the noise, right? On the final noise. So currently in the last cycles, the pipeline does a quick check to see what is the best compromise in between, what is the robust parameter that best matches.
Okay, so
both.
it's tunable.
Exactly. So it's been already a while since, if, for example, by default you choose a negative robustness, you may not have like a beam that matches the requirements of the PI. So then you sacrifice a little bit and then move towards more positive robustness. That's the latest approach. And of course, anyone that goes into the archive can download and remake following your advice. That's the idea. But nowadays, this is how, in principle, should work.
Okay. In any case, I think that one takeaway message that we could extract from here is that if your experiment is a detection experiment, so you are interested in detecting if this source is emitting or not, you are very interested in having that sensitivity, and for some reason the cleaning was not done with the optimal robustness parameter, which would be 2, then it might be a good idea, as Carmen has noticed, to redo the cleaning by setting, you will see now. So this is well, I wouldn't call it a detection either. But now if you put this to 2, look at this. Wow, that is a detection. Well, the ACA is weighting a bit much. Let's decrease the weight. And now you see, yeah, I would call it a detection. It's well, it's 5 sigma, actually. It is 5 sigma detection. But if you go to lower robustness parameters, yeah, well, more or less, I don't know, I'm not very sure. But with 2, which yeah, enhances the sensitivity to the optimal way. So this is mathematically true. So this is the optimal way to get the maximum possible sensitivity from your data, because this is what the statistics tells you that you have to do. This is the way to weight things in order to minimize the effect of noise, yeah, on the averages that you are computing on each pixel, and the way you are combining pixels. So I think this experiment, this little simulation is very nice, because it allows you to see in a critical way. It's just a detection experiment where you are at the edge of the detection, how important it is to select the right weighting scheme. Of course, this is just if you are worried about sensitivity. If your experiment is a detection experiment. If your experiment is not limited by sensitivity and you are interested in recovering a high fidelity brightness distribution of your source, you are interested in having clean PSFs, so PSFs with very low side lobes. And you would be interesting to go to the other side of the robustness space and go to uniform. As you can see, uniform, the side lobes here are very low. If you go to natural, you see, wow, yeah, the contrast that you have between maxima and minima in the side lobes of the PSF is huge. It's huge as compared to this one, to the uniform one, where you have yeah, a more peaceful sea of side lobes in your PSF. But you can see no detection at all. Uniform completely misses the source. There's no way to detect it. So what else? Yeah, what else could we do? So I was also planning, well, it's already 1 hour. So Do we still have time to play a little bit more with the data, or are you satisfied?
We have about 5 more minutes until we plan to start the Q&A section. So if you want to show another example.
Okay. If anybody wants to suggest a simulation, I was now going to show you what happens when the gains of the antennas are not well calibrated. What are the effects in the image plane, which is also fun. And with this reduced data window, you can set gains. You can set gain corruption. You can select baselines or can select antennas and corrupt parts of the experiments with phases, with amplitudes. And you can see nice effects happening in the image plane. But I think it would take more than 5 minutes to explain. So that's something you can play with. You can play with on your own. If you download there is a nice PDF in the software release where there are instructions with ideas of exercises that you can do. And let's move to Q&A.